Okay, thank you for joining us today. It's time, so let's get started. Okay, welcome to Japan Conference of the HPC Advisory Council. This conference will be our first conference in Japan. And I'm Iwatani of NVIDIA, a member of HPC Advisory Council. I will be the moderator for today. 日本の皆様ようこそお越しくださいました。本日は HPC アドバイザリーカウンセルの日本カンファレンスにご参加いただきましてありがとうございます。このカンファレンスは HPC アドバイザリーカウンセルが日本で開催する初めてのカンファレンスとなります。本日の司会進行としてです。NVIDIA から参りました、HPC アドバイザリーカウンセルのメンバーである NVIDIA から参りました岩谷が務めさせていただきます。The theme of today's conference is to make HPC Center more usable by AIST researchers. And we will hear from HPC Center and AI Center, many researcher and professor in Japan and overseas. 本日のカンファレンスとしては、HPC センターよりAI の研究者の方に使っていただくためにということをテーマとして、国内外の著名な HPC センターの先生方、または AI の研究者の方々からお話を伺います。As a big news, we will announce the collaboration between HPC AI Advisory Council and the PC Cluster Consortium, which is widely known in Japan as an HPC organization. また今回のカンファレンスの大きなアナウンスとしてですね、今回日本初の開催にあたって日本で著名な HPC 連帯である PC クラスターコンソーシアムと HPC-Al アドバイザリーカウンセルとの協業についてアナウンスをさせていただきます。Please note this conference will be held for the first time in Japan and will have both Japanese and English language into the session. 今回のカンファレンスは日本開催ということで、日本語、英語の両方のプレゼンテーションがあることをあらかじめご了承ください。なお、多くの先生方にご参加、ご講演いただくためにスケジュールがタイトになっております。ですので、各ご講演の後に、質問を受け付ける時間を一応設けておりますが、時間が足らない場合は進行を優先させていただきますことをご了承ください。So, let's get started lecture. So, first of all, I would like to ask the Gilad China, the chairman of the HPC Advisory Council, to introduce HPC Advisory Council. So, Gilad, please start your speech.
Yeah, thank you very much. Let me just share my screen. Looks like that I cannot share my screen.
Really?
It says host disabled participate screen sharing.
Okay. I'm looking for your account. Just please wait a moment. Okay. Yeah. Okay.
Magic.
I can see your screen.
Yeah, let me move things aside. Here we go. So thank you very much for the introduction. I'm Gilad China. I'm chairman of the HPC AI Advisory Council, and very proud with having the first annual. We want to make it annual. HPC Advisory Council Japan conference. I also want to thank PCCC for the collaborations and help with this conference today, and of course for the announcement that we're going to make around the collaboration. I wanted, since this is the first conference that we are holding in Japan, I wanted to explain more about the council mission, and the council activities that that gives a lot of opportunities for HPC and AI students all the way to professionals to gain more knowledge and understanding around the technologies and capabilities. So first, about the council. The council was established in 2008 with the mission to foster HPC and AI usage and understanding and knowledge. We have more than 400, probably more than 420 member companies, universities, government labs, research centers, and so forth. And we are working on multiple activities, or managing multiple activities, from best practices to university courses to worldwide competitions around HPC and AI and so forth. Participation or being a member in the HPC-AI Advisory Council does not require any payment. There is a form on the HPC-AI website where individuals or organizations can fill and join the organization. And the members can choose how much they want to contribute, if they want to contribute, and how much they want to contribute. And that can be from participation in the activities, supporting the conferences, and so forth. My main task as part of the organization is to put all of the logos, all of the members in one slide. So you can see a little bit of the breadth of the members or organizations. Again, it covers from commercial companies, universities, research labs, or government labs. Probably everyone that is using or creating technologies for high performance computing. So a little bit about our activities. Not sure I'm going to cover everything, but at least some of them. One of the activities is related to a cluster center that we are operating in California. The center includes around 13 different clusters that were contributed by members of the organization. Those clusters include variety of technologies, different kind of connectivity elements, different kind of compute elements, different kind of memory or storage, and so forth. We typically, or not typically, but sometimes we manage also to be able to host technology before it actually hit production in the market. And this provides opportunity to actually explore and experience new technologies. The cluster center is being used by the organization to develop best practices, to do benchmarking and exploration of applications. And also, we provide a free remote access to the members of the council, so they can do their own testing, their own code development or software development, their own benchmarking, their own understanding of technologies, and so forth. We also build our own platforms occasionally. For example, we build our own Lustre environment. And by doing that, we also publish the best practices on how to build your own Lustre. The results or the blueprints that we gather or build around the usage of the cluster center is published on the website and is available for everyone to learn, understand, and be able to copy the work that we the work that we have done. Our recent cluster is called Iris, which was installed just last year. And we do plan to have probably another one coming this year. I mentioned the best practices. I think one of the key activities that we're doing with the council is trying to take as many workloads, as many applications that we can, and obviously receiving requests from our members. We're doing full profiling of these applications, understanding how they work, understanding the communication patterns, the compute patterns, and then looking into the effect of different compilers, different libraries, different hardware elements, and looking on how can one optimize the performance, optimize the productivity, optimize for power consumption, and so forth. Everything that we learn, we're putting in a report, and actually we publish on the website. So everything is available for other people to review. In multiple applications, we actually have reports over multiple generations of technologies. So one can actually look on the progress of the technology and impact of new capabilities of compute, networking, storage, and so forth on the application. We also create blueprints of installing, optimizing, and running step by step. Those guides are posted on the HPC Works working group that has a lot of blueprints, a lot of best practices, not necessarily the final reports that you see on the website, which includes the performance numbers, the profiling results, and so forth. But this is more information on the different components and actually how to build things, how to optimize things from scratch all the way to have an application running. This is a really good resource for newcomers to the HPC world, or for students, for example, that want to learn the steps, or for people that build their first cluster or the first HPC or the first AI system. We're going to start with a simple step-by-step and be able to achieve great results. We're also very proud to manage multiple student-based competitions around high-performance computing, around artificial intelligence. I'll mention a couple of those. We are managing the annual student cluster competition that is done together with the International Supercomputing Conference. When in a normal year, it's done physically in Germany as part of ISC conference. Last year and this year, it will be done virtually. With utilizing leading supercomputers around the world. This year, we're fortunate to be able to have access to the supercomputer in Singapore, NSCC Singapore, as well as to the supercomputer in the University of Toronto in Canada. Those are two large systems built with a different topologies or different capabilities. So that actually will enable students that participating in the HPC-AI competitions to learn or to access different kind of supercomputers, understand the differences, and gain more knowledge. I think it's a great opportunity. The competition typically runs around running several kind of benchmarks, applications, some other missions, and help the students to gain more understanding around HPC, interact one with the other, interact with supercomputer centers. It's a great learning experience. We're also managing together with the center in Singapore an APAC AI competition that is focusing on the APAC region. Last year we had 13 teams from 11 countries or 11 regions in the area. And again, it's the same concept of having multiple tasks around applications or other benchmarks, and this competition leveraging the supercomputer in Singapore to be able to run run the tasks. I do encourage students from Japan or university from Japan to establish teams and actually participate in those competitions. It's almost a year task. So you have the preparations, we follow, we give courses, we give webcasts, webinars that give those students a lot of information around HPC, a lot of information about the applications, the workloads, why these workloads were chosen, what is being done with those workloads. They interact with us, they interact with the supercomputing centers. It's a great experience. It's a great experience as part of building the future of our HPC researchers and professionals. We're also helping and managing some courses around the world. For example, in Stanford, participating in the summer school and providing courses around HPC technology, or providing courses around RDMA programming, which is becoming the de facto programming for HPC, de facto programming for other areas. And we're happy to do that year after year. And this year we did the 8th annual programming workshop in China. We're also working with Mr. Dan Olds from ORINX and build a leadership, a student leadership list or university leadership list that actually lists all of the universities that participating in the competitions, in the activities, not just the competitions that we manage, but competitions that happen in other places. For example, the competition in South Africa, there is a local competition in China or SC competition, collecting all of their results, the achievements, and actually list the universities according to their participation and according to their achievements. If you see your local university that it's not on the list, it will be good to drive the university to participate, to build teams to participate in the competitions or in the activities. Again, this is how we foster the next generation of HPC researchers. And HPC and AI, those are the main technologies that enable us to enhance our research and knowledge and capabilities. So it's really important to expose students to HPC and AI technology. So this year we are planning a lot of activities. We are very happy and excited to have the first annual Japan conference opening 2021. We plan to have a total of around 7 conferences this year in the different places, different regions. We have the next one's going to be with together with the Stanford University in California. Later on, together with the Swiss Supercomputing Center conference, that also is going to be those two is going to be virtual held this year, unfortunately. Hopefully that by the second part of the year we'll be able to go back to physical event. We really hope so. And we plan to have a conference in Australia together with ANU, and then 2 conferences in China and conference in the UK together with the Iraq. Competition-wise perspective, we are heading towards the 10th annual ISC student cluster competition. The teams are set. We have around 12 teams all around the world, and we're going to leverage a supercomputer in Toronto and supercomputer in Singapore as part of this virtual competition. In typical year, by the way, this competition happens physically in Germany, where the students actually build their own small supercomputer or their own small system. This year, we're leveraging 2 large supercomputers. We plan to have the annual competition in APAC that we'll announce in March, and also the RDMA programming workshop and competition that we'll announce later this year. All of the information is exists on the website of the HPC-Al Advisory Council. You're more than welcome to send any questions, inquiries to our email. And of course, if you're not a member, we do invite you to become a member. There is no payment, no fees, and you will be able to be close to all of the activities. You will be able to contribute or volunteer if you think wise around that, see that wise. And of course, you will be able to access, if need, the cluster center that we're operating and other things. So with that, I want to welcome you to today's conference, and I'm looking forward to hear the rest of the talks, which looks very interesting. Thank you very much.
I thank you, Gilad. Is there any questions so far for HPC Advisory Council? Nothing? If you have a question, please write the chat or okay. So nothing. Yeah. I will go to the next lectures. The next lecture will be given the Dr. Panda Dr. Davrish Panda of Ohio State University as a keynote speech. He is very famous in the world as a MOBA pitch developer. 次のご講演ですが、基調講演としてオハイオ州立大学のドクター、ダブリッシュパンダ様の方から HPC and AI、ミドルウェア for、Exascale System and Cloud という題目で、ご講演をいただきます。ダブリッシュ、パンダさん、ドクターパンダ様は、ムバピッチの開発で世界的に有名な先生です。please start your speech, Dr. Panda.
Yes. So good afternoon, everybody. Gilad, Masaki-san, and I see a lot of my colleagues, Taisuke, Ishika. It is my pleasure to see you virtually today. Hopefully, we'll be able to meet sometime in the near future in person. So today I'll be trying to share some of the things what we have been doing. As many of you know, we have been doing this MRPitch project for many years. So I'd like to share some of the very latest things, not only for HPC, but also for AI. And as many of you know, we are in a very exciting phase. These three subfields of HPC, big data and deep learning, machine learning are trying to converge. So the question is, how do we design a software stack also in a converged manner? So in this context, I'll try to give, at least due to the limited time, I'll just focus on the two projects. Most of you are familiar with the MRPitch project. I'll try to share some of the very latest things what we are doing. We'll also be, for the last few years, we are also trying to do this high performance deep learning project, which has high performance deep learning as well as machine learning, also focusing on data science applications. And then I'll conclude it with some of the optimization and deployments we are trying to do and take our solutions to the cloud, both to the AWS and Azure. Now, this MRPitch project, as many of you know, we started almost the day one of InfiniBand when it was introduced in October 2000. We are very proud to celebrate 20 years of this project. And over the years, it has grown into a lot of different versions. Currently, there are more than 3,000 organizations in 89 countries using this. Last year, actually 2020, we crossed the 1 million download mark. So currently, we are at a 1.2 million downloads just from the OSU site. Of course, our stack is integrated with a lot of software stacks of many other vendors, Linux distros. We don't keep track of those. But it is also empowering a lot of top 500 clusters over the years. Almost like for 16 years, we are working with a lot of top 500 systems to get a very good performance using this software stack. So this tries to show the overall architecture of the MRPitch software family. So not only we focus on MPI, we also focus on PGAS, hybrid MPI, MPI plus X, MPI plus PGAS. And And of course, we try to support all the different networking technologies. Over the years, we started with InfiniBand, but focusing on IWA, Procky, OmniPath, and Elastic Fabric Adapter. And also working on all the different kinds of the multi-core, many-core architectures. And but the core thing is our designs, which are in the communication runtime, trying to take care of all these different components. And then we not only carry out research and publish these papers, but we also take them into an integrated solutions and then make it available to the public. So today, mostly I'll be talking about these three packages we have: MAPIS2, which is the base version, which is the MAPIS2X, which is the advanced version, and especially MAPIS2 GDR, which is the GPU specific version. And especially these two versions are not only targeted for HPC, but also for deep learning and machine learning. So I'd like to try to show some of the latest numbers what we have. Of course, many times, as you are seeing, the system sizes are continuously increasing. If you think of like the Fugaku system, it has like 7.63 million cores. So always, anytime you are trying to run an MPI job, the question is how you can start. I mean, just starting an MPI job itself is a big challenge, and continuously we have been working on that. So here these are some numbers from the latest TACC Frontera system. So here, if you see like almost like a 230,000 process, we are just able to start like just in 31 seconds. And this is on like a 4,000 nodes. We are able to start the MPI job and it starts running. And then that is not the startup. We try to focus on all the different components. So let's take an example here. As you know, InfiniBand has multicast, hardware multicast. So the question is, can we take advantage of that? Try to do actually MPI bcast. So this is again taken on the on TACC Frontera up to like a large scale of nodes. Here, if you see like it is a 1K node. So this is basically the software solution, but this is the hardware-based solution. So as you can see, you can almost get a factor of 2x improvement by trying to trigger these hardware multicast. So these are all our options in the design. So based on your systems, you should be able to trigger and take advantage of it. Now, these are the results with SARP. As many of you know, Mellanox and now NVIDIA have the SARP module. So we have done a very tight integration of our MAPIS2 library. In this case, I'm trying to show MAPIS2X, which has some advanced design. And that has a very tight integration. And this, I'm trying to show the numbers here. If you see, this is on the full scale TACC system. It has 7,861 nodes. This is one of the largest experiment we have done with our MAPIS2 library and with SARP. So here you can see like this is our basic MAPIS2 version, but with our optimized SARP, you will be able to almost like all reduce, MPI all reduce, you will be able to improve by a factor of 5, MPI barrier by a factor of 9, and also here MPI reduce by almost by a factor of 6. So these are again, all these are runtime parameters. So depending on your system, you should be able to configure and then try to take the best performance. Now, these are some of the very latest numbers. We have the latest release has the support for the ARM A64FX. This is very similar to the Fugaku, but the only difference is that this is with InfiniBand. And as many of you know, this is the Ukami system at the Stony Brook in US. So these experiments have been run there. So here you can see we are trying to show the numbers between MAPIS2X and OpenMPI. These are the internode latency. Intranode latency, we perform very well as the message size increases. Bidirectional bandwidth is very similar, internode. Here you can see like a bcast. This is actually in a log scale. So we perform very well compared to the latest version of the OpenMPI on this system. Now, those are the kind of the pure host-based systems. As you know, we have been working on this CUDA-aware MPI, which the concept which introduced in 2011, and a lot of other libraries have adopted those. So these are some of the numbers on the x86 system. Here you can see like from a GPU to GPU over the network, we are able to send data at the 1.85 microsecond, and that gives a very big performance boost for also the internode bandwidth as well as bidirectional bandwidth. And with the very latest release, now we have supported the AMD GPUs also. So this is the release we made before the holidays. If you have not used these, please feel free to use, download this 235. So these are with the ROCm support, that is from the AMD GPUs, supporting the similar kind of RDMA, GPU direct RDMA with their ROCm library. So here again, we are comparing with our MAPs to GDR latest version. As you can see, this is intra-node, like the two AMD GPUs talking to each other. These are MI50 GPUs. We are able to communicate at 1.77 microsecond, and inter-node across InfiniBand, this is around 3.44 microsecond. But we have also optimized the collectives on this system. These are trying to show 8 nodes, 8 GPUs. So here, for example, 64 GPUs, we are significantly doing better than OpenMPI version. Similar kind of things are also for the Bcast. And as many of you know, the next generation, the Frontera, which is the exascale system from Oak Ridge National Lab, will be having these AMD GPUs. So you can try to expect this kind of performance from these systems. So those are on the pure MPI side. So now let me move into the high performance deep learning and machine learning. So the problem, as many of you know, again, in the deep learning machine learning, there is a lot of focus on collectives. How do you optimize the collectives? How do you optimize the communication? So what we have done here is, instead of like using any other library, we have come up with a MPI driven infrastructure. And in this case, I'll be trying to show especially our MAPIS2 MPI-driven infrastructure. So if you have installation of our MAPIS2 library, you should be able to run any of these deep learning frameworks, TensorFlow, PyTorch, MXNet. You don't need any other library. So what we have done a tight integration with Horobot. And in the left-hand side and right-hand side also for PyTorch has different runtime like torch distributed, deep speed. So everything has been integrated. We have this new project, high performance DL. So if you just go there and download the user guide, it exactly tells you step by step to how to take our MAPIS2 libraries and link up with this middleware, and then you are ready to run all your applications, deep learning and machine learning applications. And below this, what we have two solutions for you. If you are using pure CPU, you can use MAPIS2 or MAPIS2X. If you are using the GPU, you use our MAPIS2 GDR. So with this, let me show you some numbers from these libraries. I'll try to show some CPU-based deep learning, GPU-based deep learning. We are also trying to focus a lot on out-of-code training, exploiting hybrid parallelism, data and model parallelism. I'll try to show an AI-driven digital pathology example. And very recently, we have also taken the same framework, and we are trying to also optimize TACC, which is a more like a data science applications, and some machine learning applications. So this is trying to show the numbers from TACC Frontera. It's the distributed TensorFlow. It is a purely CPU-based deep learning. Many people say that, yeah, that is not good, but you still get good performance if you have an access to a system like TACC, in this case, like a 2000 CPU nodes with 114,000 cores. So you can see like we are able to give you very scalable performance. Here we are getting like almost 260,000 images per second. And we are able to train ResNet 50 on these 2048 nodes in just 7 minutes. And of course, there's a lot of focus on the GPU side. So here, many of you know, like a lot of deep learning applications, the performance is very much dependent on all reduce. And of course, NVIDIA has the Nickel library. MPI library developers have also been optimizing all reduce for many years. So here, I'm trying to show on the DGX2, just at the all reduce level. As you can see, like MAPIS2 GDR is able to deliver far better performance than Nickel. These are for small and medium messages. Even for the large messages, we are able to do very well. And this is at a larger scale. This is the Oak Ridge Summit, who is used with the number 1, and now it is the number 2. The same story holds good. This is MPI all reduce at scale. We are able to these numbers are up to 1536 GPUs. And as you can see, as you are with the different message sizes, as the number of GPUs are increasing, we are able to actually deliver far better performance compared to Nickel. Also, the other libraries like OpenMPI and Spectrum MPI. So then this is the distributed TensorFlow. Those are the all reduced numbers where it is the distributed TensorFlow. So here we try to run ImageNet 1K has 1.2 million images. And here we are able to totally like train these in just 4.5 minutes using like a 1536 GPUs. As you can see, we are able to get very good scalable performance as the system size is scaling. We also ran a lot of experiments on the Lawrence Livermore Lassen system, which is very similar to Summit, but instead of 6 GPUs, it has 4 GPUs. And here you can see, based on that integrated framework I indicated, this is the PyTorch with all these 3 torch distributed or forward or deep speed. We're able to compare with the nickel, and you can see compared to nickel, we are able to deliver almost like 10,000 images per second faster. So what this says that if you really are looking for a very high performance deep learning, you should be able to utilize our MAPIS2 GDR library and should be able to get very good performance. So those are some of the basic deep learning, but as many of you know, as the model sizes are increasing based on the limited GPU memory, the community is facing this issue of out of core. And especially like data parallelism will not work there. You can move to model parallelism based on your memory size. So this is the reason where only you can do it with a model parallelism. But model parallelism is very hard to program. So we have introduced some different framework. One is a hyperflow, which we presented at the AIST 20. And then we extended that, and this paper we presented at the supercomputing in November. So here we took a very concrete example, like we have been working with a pathologist at the Ohio State. So especially pathology examples, they use very whole side images. So it is like 100,000 by 100,000 pixels. So they were actually running, many of these pathologists were using only in one node using one GPU. It was taking 32 hours for them. And they didn't know how to parallelize these large messages. We worked with them and actually using our hybrid parallelism, which is called a GEMS. Using that framework, we're able to reduce just with 4 GPUs, we're able to cut down the time by 4. And then we scaled to 128 GPUs, almost like 27 minutes. So we gave almost 64-fold improvement. And now they are ready to actually go and then look for very complicated models. They were not able to dream even to go into those kind of levels, but with this kind of our solutions, they are able to now take a big step. And then recently, we are taking the same approach. I'll try to show the DASC and QML. The DASC is the new data science application. Some of you might be familiar. That is getting a lot of importance. So currently, they have solution is there with the UCX. So what we have done again with our converged software library idea, we have introduced an MPI for DASC, and that goes through an MPI for Pi module and then linked with the MAPIS2 GDR. So in fact, just a few hours back today, US evening and morning, we actually made the first release. MPI for DASC, we have made a new release. Some of you would have got that announcement. So here I am trying to show some numbers, some of QPi array and its transpose. So as you can see, compared to like IP over IB or UCX, we are able to significantly benefit. Here it's almost 3.47 or 6.92 times better performance we are able to give with our tight integration with our MAPIS2 GDR library. This is on the TACC Frontera GPU subsystem. There again, we are able to give you almost a factor of like a 3 improvement. So if you have been using like a DASC, please feel free to download this new release, and you should be able to boost your performance significantly. Same thing we are also trying to do with the QML. These are the machine learning applications. We have taken this MPI for Pi and then MAPIS2 GDR. Again, done a tight integration here. These are some of the numbers like a k-means, nearest neighbors, linear regression. As you can see, we're able to give almost like a 1.6, 1.2, 1.4 improvement. This we presented at the MLHPC workshop. In another few weeks, you will see a release coming out from our group. Again, you should be able to try to take our solution and then extract higher performance. So these are for the very dedicated systems. As you know, a lot of workloads are moving into the cloud. We are working very closely with both Azure and AWS. So if you go to the Azure, we already have our basic MAPIS2 and MAPIS2X running there. All these different CentOS HPC images are available. As long as you have an account, you should be able to go to this page and then utilize the thing. And here I'm just trying to show one example, which is the WRF, weather forecasting between MAPIS2 and MAPIS2X with XPMEM. You can actually get higher performance. And similar thing, what we have done is AWS. AWS, as you know, it doesn't use InfiniBand, but it uses your Elastic Fabric Adapter, which also uses like RDMA kind of concepts. So we have done a new design for AWS, which runs on the EF adapter. And here I'm trying to show some numbers on the MVAP/X AWS. These are again publicly available releases. As you can see, this is OpenMPI, Intel MPI, and our MVAP/X AWS. As you can see, we are able to scale actually with the more number of processes. So if you are using any of these cloud, you should also be able to utilize our MVAP/2 library and get this kind of performance advantage. So those are happening on the OSU side. I just want to talk a little bit, few minutes about this initiative. This is actually, we have started from 3 years back. This is a commercial spin-off. In fact, xScale Solution is actually a sponsor of this event. If you see the webpage, we are a sponsor there. And through this commercial spin-off, we are actually able to now provide commercial support. Many of the HPC centers, they actually want dedicated response optimization of the application. So we are able to do all these things. In fact, we are working with some leading national libraries and as well as international supercomputing centers. And if any one of you are interested or any organization interested, we'll be happy to talk with you. We are also, based on the basic MVAP/2 library, which are available from OSU side, we are also building advanced packages. This is an xScale HPC package. So in fact, here we have now a new solution using the Mellanox Bluefield offload. And we have a solution which can actually optimize a lot of non-blocking collective communications using the ARM process on the Bluefield NICs. So if you are again interested, please feel free to contact us. Similarly, we have another product called xScale AI. So many times when you are running the deep learning application, you don't know where the performance loss is taking place. So here we have actually done an integrated profiling and introspection support. We call it deep introspect. So just visually, you should be able to see what is happening not only from your applications to the really network level. And then you can exactly see that, okay, this is where the already used performance got slowed down. Or this is where a lot of already used messages are going on. So by looking visually, you should be able to actually optimize your stack. So once again, these products, these are the commercial products which are being available through xScale Solutions. If any one of you are interested, we'll be very happy to talk with you. So with this, let me conclude here. As we know, like the upcoming exascale systems and cloud need to be designed with a holistic view of HPC, big data, deep learning, machine learning. And here I just focused on the HPC and deep learning, machine learning. As many of you know, we have done a lot of work on big data. We have the RDMA Hadoop, RDMA Spark. Now we have a new project to bring all those stacks to MPI layer again. So eventually you just need an MPI library and then you should be able to handle all these things. So that project is running now. Might be in few months, you will see some new releases coming also from that angle. And once we have these kind of solutions, this will actually enable us to go into the very large scale system, not only exascale systems, but the next generation zetascale systems. So let me then thank all our sponsors, but more importantly, these are all my heroes. What I just presented in 20 minutes is actually a work of 20 years by a lot of students, staffs who have graduated and working all over the world. So I'd like to give my thanks to all of them, on which we are continuing over the years. So with this, let me stop here. These are all our web pointers. If you have any quick questions, I'll be very happy to answer. You can post it in the chat. Otherwise, please send me an email and I'll also be able to follow up with you. Thank you. Any questions?
So thank you for Dr. Panda. I turn off the all of the mic shortly. Yeah, if you have any question, please set question shortly.
There are 2 questions for Dr. Panda in the chat window.
Okay. So I'm reading it from Jim Leong Chin. For AMD ROCm benchmark, is it 1 MPI process per GPU? Yes, that's correct. That's correct. And also I forgot to indicate, like many of you might have used the OSU micro benchmarks. So now we have actually a ROCm version there. So you should be able to, that we also released with the latest MVAP/2 GDR. So you should be able to utilize that for any systems. I use that benchmarks to show the numbers. Then there is a second question, is it possible to get MHPC into the AWS Linux 2 image? We have been working with them, so please talk to them. Again, what we have done, we have gone through a lot of discussions. They are looking for demands. These are, the commercial cloud providers. So as of now, we are providing from our website, and so that if you have an account, you should be able to download and build it. But they are actually talk to me sometimes saying if people are really interested, they should contact them, and hopefully through that process, they can actually make the images for us. The Azure people have done it, but not yet with the AWS people.
Okay. Are there any questions so far? Nothing? So going to the next. Sorry?
Thank you. I said thank you again, and look forward to the other talks.
Okay, thank you, Dr. Panda. Okay, so we're going to the next speech. So next lecture, the Professor Boku will give lecture entitled HPC for AI, AI for HPC. Time to meet together as next key speech. He is Doctor at the Center of Computational Science, University of Tsukuba, and also Deputy Facility Manager of JCHPC。次の講演は2つ目の基調講演として、筑波大学計算科学研究センター長であり、JCHPC の副施設長であられる、ボク先生の方から、ご講演をいただきたいと思います。So please, Boku-san, start the presentation.
Okay, can you hear me?
Yeah, I can hear you.
Okay, thank you very much. So good afternoon, everyone. My name is Taisuke Boku from the University of Tsukuba. And as Iwatani-san introduced, I'm currently the Director of Center for Computational Sciences, University of Tsukuba, as well as Deputy Director of the JCHPC, which is a joint organization between the University of Tsukuba and the University of Tokyo. And as a third hat on me is that I'm also the President of the HPC-Al consortium in Japan. But my talk is relatively close to the one of the researcher on the HPC. So thank you very much for giving me this wonderful moment. And I'm especially like to, I'm very glad to see DK in about 1 year of our break. So today's my talk is focusing on the HPC for AI and AI for HPC, entitled Time to Meet Together. So before my talk, I must confess that I'm not a specialist or a researcher of the AI. I'm the researcher on the HPC. So please understand that today's my talk is a very general talk and a sort of the lab call to AI from HPC research. So this is just a background of my current institute. So Center for Computational Sciences, or CCS, University of Tsukuba, has about 30 years of the history as collaborating fields between the application researchers and system researchers. So we have currently 45 of the faculty staffs, and about 2/3 of them belong to the any domain science like astrophysics, particle physics, material, life science, and the climate. And on the other hand, another 1/3, including me, are on the system scientists like HPC system or database and image processing. So we are one of the supercomputer center under the MEX, but we are originally the research center, not the service center. So this picture shows that our latest supercomputer, which has been running almost 2 years in past, is named Cygnus. So this is a world first practical supercomputer with multi-hybrid accelerating architectures. So we have 320 of the A100 GPUs and 64 Stratix 10 FPGA by Intel. So it is a really hybrid system of the mixture of the two kinds of the accelerators. So we are now searching for some good use the combination of the GPU and FPGA for the both HPC and AI. Okay, so let's look back very briefly about an HPC system's key technologies so far. So we have about 50 years of the history in the HPC technologies. But then, of course, in the first stage, the vector processing architecture was the main player. And they're just focusing on the numerical computing and the array computing. And most importantly, they're supported by the high memory bandwidth rather than the vector processing. So there is some misunderstanding that the vector processor architecture is good because they have a vector pipeline. That is wrong. The goodness, it came from the high memory bandwidth. So that is totally different from the scalar processor. But from the early 1990s, the mass parallel system, especially the PC cluster, which plays the main role under another HPC world. So there, they introduced a large amount of the highly cost-effective CPUs, but the CPUs, of course, ordinary CPUs has a relatively low memory bandwidth, and cache hit ratio is really a crucial issue. And another important things here improved is that the interconnection network. So there in that by the thanks to the PC cluster architecture, so many of the interconnection network became the commodity. At that time, it was called storage area network or a system area network. So including the Mininet, Ethernet, and InfiniBand, and so on. So today, as you know, that the InfiniBand is the most important player in the commodity interconnection network. And as Professor Panda mentioned, that an MPI is a really important tool for the distributed memory computing. So after year 2000, finally, the CPUs entered to the era of the merge core and the onboard shared memory system, so-called NUMA, non-uniform memory architecture system. So even in one socket, so 2 to 4 cores per CPU as a begin, and now we have up to 72 cores of the KNL. And more powerful CPU core is now available around 48 to 64 cores per chip by their Fujitsu and AMD and so on. So there, we have a very good number of the cores when we connect multiple sockets on board by the NUMA technology. And finally, the accelerator is leading the PC cluster world now. So it started with something like a clear speed and a GPU. And original many core architecture of the Intel was also the accelerator called the Knight's Corner. Well, in another, so there, I like to summarize that an HPC technology contributing to AI, so that in the viewpoint of the computation. So before that, of course, you know that today's deep learning and AI is based on the neural network processing. So in my understanding, it started in early 80s or maybe a little bit earlier. So the neural network started to study for the very good machine learning scheme. But at that time, the GPU performance is very poor. So I remember that, for example, even the 16-bit or 32-bit microprocessors in the early 1980s was just is lower than the 10 megahertz of the CPU frequency, and of course single core and the single instruction execution. So there was no special hardware to support the neural network. And I remember when I was a student, the neural network at that time has only 3 layers. So input, output, and one layer of the middle layer. So there, as a result, the result is not sufficient because there is no enough power to support such a very large amount of the computation. So that is not deep learning. So deep learning means a deep layer convolutional neural network-based machine learning. So it is not deep. It is quite shallow learning. So after that, accelerators, especially GPU, greatly supporting to their to start to support the AI and deep learning. So after GPU became attractive, at first it was attractive for the HPC, traditional numerical computation by the floating point. But after that, maybe less than 5 years, so GPU is a really interesting and attractive device for the neural network and the deep learning. So Basically, the deep learning technology, like a neural network, is a very regular and large capacity of the computing. So it is quite suitable for the SIMD implementation and the future of the GPU. And finally, today's some GPU makers are shifting their focus not from the traditional HPC to the AI. So NVIDIA is one of the most advanced company to shift to the AI, in my viewpoint. And AMD and Intel follows it. And CPU instruction set is also changed, modified for the AI applications, like an FP6 for the deep learning. FP16 and the bfloat16 is now available on the most advanced CPU architecture. And here again, the SIMD vector instruction feature was originally introduced for the HPC, but now it's available for the AI with up to 512 bit of the width. So let's think that how the GPU is shifting to the AI. So GPU is now the key technology for deep learning. And here is I show the chart of the performance improvement of the NVIDIA GPU from Pascal, Volta, and the recent Ampere architecture. So of course, the number of cores increased, but then recently, especially for the half precision and single precision computation is strongly enhanced by the NVIDIA. So you can see that FP64, double precision for traditional HPC, the Pascal to Volta has just 1.5 times improvement, and Volta to Ampere is only 1.4 times. But on the other hand, in the deep learning by the tensor core for the AI application, the Pascal to Volta is 6 times because Pascal has no tensor core. And after that, the Volta to Ampere is 2.8 times because it is both by the tensor core, but there are about 3 times faster performance. So it seems like the GPU is largely shifting to the AI deep learning more than HPC enhancement. And in my personal impression, the AMD GPU, they're represented by the MI100 and the next MI200, are relatively balanced, so balanced between the HPC application and the AI application. So today's trend of the HPC systems toward AI applications. Of course, a PC cluster is older GPU ready for the AI and HPC. And as you see here, the world's largest GPU cluster summit by Oak Ridge National Laboratory by the IBM Power CPU plus an NVIDIA's Volta GPU, and also the ABCI system. That is the largest GPU and the AI system in Japan by the AIST, and they also introduced Volta, and recently they announced some enhancement of the ABCI by their Ampere GPU. And on the other hand, MPP system like Fugaku is also focusing on the AI. So A64FX CPU is now ready for the FP16 half precision computation. So I was a member of the working group of the architecture discussion of the Fugaku so far. And in the midpoint of the architecture design, so we discussed about the introduction of the FP16 to Fugaku because the Fugaku must work also for AI as well as the traditional HPC. So now most of the CPUs are ready for the FP16 also for AI deep learning. And another system software interesting point for the ABCI, in my viewpoint, is the container technology. So you know that most of the AI researchers are not experts of the HPC system or PC clusters. So the container technology is one of the key issues to make them the easy to use of the system, even for the novice researchers of the HPC. So AI research is very important and must be very easy to use for these researchers. So, and I think that the ABCI is strongly considering about the container from the beginning. Okay, so the next, of course, there are many talks or many stories about collaboration with HPC and AI. So here I saw one example. So they're using the deep learning technology to their climate. So the first, they make a very large scale globe level of the simulation, then detects some source of the typhoon or hurricane or cyclone everywhere in the world to find out that makes a big impact to the human life and before it happens. So that is a sort of the deep learning application based on the HPC application. And here they treat about 3.5 terabytes of the climate simulation data for the deep learning. But I think this is just an example of the using AI for the result of the HPC. And nowadays, I'm considering the much more deep relation between HPC and AI. So my topic is that how the AI contribute to the HPC. So far, HPC greatly contributed to AI in the technology. There is no doubt. So I'm thinking about the relation from the HPC side. So now it's time to pay back. So how the AI can pay back to HPC on the opposite direction. So what is the strategy for the AI technology contributing to HPC? So there are many stories, but I think the most simple scenario or a general example is that. So in the HPC application, we must calculate the very large, wide space of the parameter-based simulation. That is not the capability computing. This is the capacity computing. So we must run millions of the cases to reach to the result for the searching the parameters. So there we have a very high degree of the searching space. It is almost impossible to search out for the everything. So in many cases, for example, climate or life science and the material science, whatever. So the expertise of the researchers look at some intermediate result of the simulation. Then they will try to find out the next target of the parameter set. So it is basically by human brain and the intuition. So you know that an AI and deep learning can be replacing the certain human brain and the intuition into the machine learning. So I think that this is one of the very easy and a very practical way to apply the AI technology to HPC. And actually, so many people are starting to building the system for a cooperation by HPC and the AI together. So I like to show the one example. This slide borrowed from the University of Tokyo, Professor Hanawa, that there are new plan to introduce a new system for the HPC and the AI. And the machine is called the Wisteria VDEC-01, and that is very recently announced by University of Tokyo. And the system consists of the two parts. One is called Odyssey. That is basically the Fujitsu's MPP system, a sort of the miniature system of the Fugaku with about 5% of the Fugaku's resource capacity. And the other side is a deep learning or data learning system, which is named Aquarius, based on the NVIDIA A100 GPUs. So you can imagine that Odyssey and Aquarius came from the story of the Apollo 13, as you know. So their idea is almost the same as my thinking, that doing the simulation and the deep learning and with a sort of the eco cycle that the simulation cause and make the result, and it is processed by the deep learning or machine learning, then makes another set to calculate and the simulation again, and so on. So it is very similar to my thinking. And another one, so I'm sorry for the Japanese slide, but then I think that most of today's audiences are from Japan. So I borrowed this slide just a couple of days ago from the Professor Yasushi Okuno from Kyoto University. So he's one of the very famous guy now using the Fugaku system for the COVID-19, the medical applications. So the analysis of the molecule and find out some medicines. So he said, recently I listened to his talk about data science, AI, and the simulations relations. It is the same scenario that so using the supercomputer for the simulation of the molecules, and then of course it is impossible to search all the field or all the candidates. So there are some shrinking the such field into some very strong candidate by the AI technology, then simulation again, and get the result again. So that is a very important new scenario for the MD simulation. And this is also sorry for Japanese, but I borrowed these slides and I cannot touch anything for this slide, just as is in the Professor Okuno's presentation slide. So first, they have some amino acid array and have a deep learning here and screening some special case, which should be the target of the molecular level simulation. And do the molecular level simulation like an MD and other applications. Then finally makes a protein 3D folding model. And getting back in the back propagation. So the result is going back to again to have more precise deep learning and more precise targeting and the simulations going on. So such he said that currently this framework is called AlphaFold. And currently the deep learning part and the simulation part are separated. But he said that it should be merged in finally to make a very good research style. So this is summary of my talk because I have just 15 to 60 minutes. So I like to say that HPC system technology has been built more than 50 years. And we have been, HPC guys contributed to makes the AI system very good one, especially for the accelerator technology and the interconnection and the PC cluster building, everything. Now the AI is one of the latest important application for the HPC to make a big impact to the human life. And HPC technologies have been contributing, but now I think it's a time for the payback to how AI application or technologies contribute to the HPC solutions. So we can share best technology. Fortunately, we can share the technology, knowledge, and hardware and software, everything. And then some people started to making a combined multi-purpose system with a good balance between the traditional HPC and the new AI applications collaboration. So that I think it is a sort of the HPC AI ecosystem, and which is one of the most important targets for us from both sides of HPC and AI. And then finally, I'd like to announce that very briefly that the University of Tsukuba also will start very soon our new solution for HPC AI ecosystem by our own system. I cannot tell anything in detail, but this is just an announcement from me. So let's do it. Thank you very much for your attention.
Thank you for presentation, Professor Boku. Unfortunately, currently, so time is delayed. So I would like to go on the next program. So if you have any question, please mention that in the chat. So in the next lecture is Mr. Sato, the chairman of the PC Cluster Consortium, which is a very famous HPC community in Japan. As I mentioned in the opening session, we will announcement of the collaboration between the HPC AI Advisory Council and HPC Cluster Consortium. Before this announcement, he will introduce the PC Cluster Consortium activity. So please start presentation, Sato-san.
So thank you for a nice introduction. So can you hear me? Okay.
Yeah, I can hear you. Yeah.
So as announced by the Iwatani-san, that I'm very glad to the announcement for the alliance between the PC Cluster Consortium and HPC AI the Council. So in my presentation, I'd like to introduce our PC Cluster Consortium and activity. So currently, I'm a chairman of the PC Cluster Consortium, and also I'm belonging to the RIKEN, the Center for the Computational Science, and the University of Tsukuba. So let me start with the background. So the word, the PC cluster, this is the rather old word, but this means that the parallel system using the microprocessor. That kind of system is now indispensable IT infrastructures for modern societies, not only for the HPC targeted the scientific technical computing, but mainly for recently many people is interested in the big data technologies and also AI and machine learning, such as the deep learning. So that kind of system, the PC-based parallel system is the main infrastructure for the big data and AI and the AI machine learning. And also, the PC Cluster Consortium is interested in high-performance computing. So high-performance cluster is commonly known as the very promising technology for high-performance computing up to the exascale computing. So the member of the PC Cluster Consortium are challenging for exascale computing. Actually, I and ex-chairman Professor Ishikawa are working for development of the Japanese flagship supercomputer in Fugaku. So what is the PC Cluster Consortium? The PC Cluster Consortium is the non-profit organization, and we are aiming to contribute the whole HPC market from low-end user to the high-end researchers. So we are going to contribute that community through the development and the promotion of the PC cluster technologies. And recently, we are also interested in emerging accelerator technologies, which is attached to the PC cluster. So, and that's the PC cluster consortium is established in almost 20 years ago. So 2021. So, and the PC Cluster Consortium has been supporting the dissemination of the various open source softwares and PC cluster technologies. And it is useful to realize high-performance computing and also it's contribute to the PC cluster market through the several activities of the member. So let me introduce some history why PC Cluster Consortium was established. PC Cluster Consortium established mainly for dissemination of the outcome of research result of the real-world computing project, the RWCP, that is funded by the Japanese Ministry of the Economy, Trade, and Industry, that is METI. The project is were carried out from the 1992 to the 2002. So it's a 10 years project. So in that project, the RWCP has been developing the technology of the PC cluster. So that is the parallel system using the modern microprocessor. So, and the highlight that of the project is that in 2001, RWCP demonstrated cluster which consists of the 1024 Pentium 3 processors, and these were connected by the Mininet. That is high-speed interconnect, and it's achieved almost 600 gigaflops in DIMPAC. At that time, this is the very surprising record, and the world biggest and fastest PC clusters at that time. So to realize and to make that kind of the clusters, so RWCP is developing the S-core cluster software. So that is the cluster management software and provide the high performance and providing interesting and useful capabilities, including the efficient communication layers on top of the Ethernet, gigabit Ethernet and MILNET, and the time sharing scheduling for the power system, and the checkpointing and restart function. So from more than a decade, the SCORE research and development has continued by support of the PC Cluster Consortium. So currently, we have the 22 corporate members shown in this slide. So newest one is the ARM company. So, and many majors, the computer vendors and the company is joined our PC Cluster Consortium. So let me talk about an organizational activity up to the 2020, so this year. So main activity is that organizing annual PC Cluster Symposium and workshop once in a year. And also that we are supporting the working group activities for system software development and languages and practical application software promotion. And recently we started working group HPC open software the dissemination. And we have the working group for the public creation. So let me talk about then more little bit detail of the working group activities. So system software development working group is developing the system software which the useful for exascale computing. So in this group, the two kind of software is promoted. So one is the MSC kernel. That is the lightweight kernel, and it is very useful to the removing the jitters, operating system jitters, for the large scale system. So and another the software is the process in process. This the middleware is providing the very interesting the execution model between the thread and process. So and Excalibur MP programming language specification working group is the activity for standardization of the programming language called Excalibur MP. So Excalibur MP is a directive-based PCAS language based on C and Fortran. So and this the language is supporting two kind of the programming model. One is the global view, which is inherited from the high performance Fortran, and also this language is supporting the query function as a local view programming. So this group is doing the activity to standardize the specification of this language within Japanese HPC community. And practical application software promotion working group is a working group to fill the gap between the state of the art, science, and the engineering computation and users. So sometimes the end users has a difficulty to use the recent and modern the parallel system. That's promotion working group is helping organizing the event to help the users to make use of the very advanced the simulation and the scientific software. And last one is the HPC Open Source Software Dissemination Working Group. This is the new one. This working group is started 1 year ago. And this group is going to promote the open source HPC software, especially the software which is developed by Japanese post-Petacrest project. So it's include the compiler and PIP and MC kernel and the advanced communication library. And this year, the last year, 2020, I took over the role of the chairman of the PC Cluster Consortium from the Professor Yutaka Ishikawa. So, as it's the 20 years since from the founding, the consortium has been established the new management policies to contribute the two things. So the contribution for technology development of the system design and the utilization of the HPC cluster based on the PC the technologies, PC server. And also we are interested in the promotion of the market development and for IT system based on HPC cluster technologies. Of course, it's include the big data technologies and machine learning, the deep learning. This is the emerging technologies to make use of that high performance cluster. So at the year of the 2020, the last year, based on this new management policy, we started discussion to reorganize the working group and developing the attractive the activities for the new years. So especially, we are much interested in extending the HPC open source software working group, as including Japanese-made open source software, and also the software which is developed by the United States and Europe. So, and the PC Cluster Consortium is agreed the alliance with the HPC-Al Advisory Council. So, HPC is the main technical field in the PC cluster technologies, but recently many people is interested in AI and deep learning and big data as the emerging technologies. I think the PC cluster. So this is again this is the old world, but microprocessor-based IT infrastructures and platform is very important for these emerging technologies, such as the deep training platform deep learning. So I believe the alliance of the HPC Cluster Consortium and the AI HPC-Al Advisory Council will contribute the strength of our activities in the future. Thank you for your attention.
Thank you very much, Sato-san. Okay. Yeah. Okay, go on to the next. So from now, I would like to announce collaboration for the PC Cluster Consortium, HPC Advisory Council. So Mr. Sato-san, chairman of the PC Cluster Consortium and HPC Advisory HPC Advisory Council, the chairman is Gilad China. Please say the short speech from now. So, Gilad, please speech for this announcement.
Yeah, I'm very happy to. Thank you very much for the kind words, Sato-san, and I think from the HPC Advisory Council, we are very excited to collaborate with PCCC as part of our mutual mission. I think there is a great commonality between our vision, the things that we're doing, and it will be great to combine forces as we're driving things moving forward. From the concept perspective, we are very happy to look into different kind of elements that will be part of the collaborations, and I'd like to mention a few of those. We will be continuing to collaborate around conferences and workshops. I think today it's a great example, and we plan to continue with conferences and workshop and be able to share presentations and share vision and bring more knowledge and more technology overviews to more places. So that's something that would be a great thing for both of us. The second thing, as part of this collaboration, we will enable also access to the HPC Advisory Council Cluster Center to PCCC members. Of course, PCCC members are welcome to join the HPC Advisory Council. There is no membership fees and things of that sort. But as part of the collaboration, if you are a member of the PCCC, you will have the same advantages as being a member of the HPC Advisory Council, and that will include access to the cluster center, the system center for testing, benchmarking, development, and so forth. We will also collaborate around university programs to be able to offer the courses that we are having also to universities in Japan. And last and not least, we will collaborate and try to organize a Japanese university team that will participate in the student cluster competitions. I think the competition is it's a great experience for students. It's definitely a learning vehicle. It lasts for multiple months, and during that time, there are different courses and lectures and hands-on understanding of HPC and AI technologies from the hardware perspective to the software perspective to running applications, to see how HPC and AI is being combined together and so forth. So it's a great opportunity. And we're seeing students that participated in competitions in the past becoming leaders in the industry, leaders in research, and so forth. So it's a great experience. We didn't see so many or too many teams from Japan in the competition, and we think it's a great opportunity. And this is something that will work together to try and establish a Japanese team. Again, Sato-san, I'm very happy and excited with collaboration, and I'm looking forward to be able to drive more of our vision and activities together.
Well, thank you for your word. And again, we are very happy to for the alliance with the HPC AI Advisory Council. So, and as I presented, so from this year, we are discussing in a new direction of the PC Cluster Consortium. So far, we are much from the historical reason, we are much focused on kind of the specific software the languages and HPC, the system software. But the new direction will be the cover more the wide range of the open source software. And I think we want to much contribute to the dissemination of the open source software, especially which is developed by the Japanese communities. Of course, we are interested in open source software which is developed by the United States and Europe. But one of the mission, the PC Cluster Consortium Japan, as the Japanese communities, we are interested in extending the activity of the Japanese open source software. So, and maybe this alliance is very useful to communicate within the Japanese open source software for your community, the HPC AI, the advisory council activities. And also, I would say that we want to work as the bridges between the HPC AI Advisory Council and Japanese HPC communities, like the Japanese university computer centers, and also the Japanese computer vendors. So again, I'm very looking forward to the future collaboration with the HPC AI Advisory Council. Thank you.
Okay, thank you for announce each chairman. So 本日の発表としましては、一応 HPC アドバイザリーカウンセルと、PC クラスターコンソーシアムは今後いろいろな面で協業させていただくということになります。どちらもコミュニティですが、今後いろんなコンペティションだとか、またPC クラスターコンソーシアムがやっているワークショップ、またシンポジウム等で、HPC アドバイザリーカウンセルと、良い関係で、HPC、そして AI の、発展に寄与したいというふうに考えております。どうぞこれからもよろしくお願いいたします。
こちらこそよろしくお願いいたします。
それでは、So from now, take a break time about 5 minutes. Sorry, basically the 10 minutes, but it's delay. So next, we're from 3:40. Thank you. ここで、10分というか、ブレイクタイムを取れます。次回は15時40分から、始めさせていただきます。時間が押しております。申し訳ございません。よろしくお願いいたします。
はい、岩谷さん、こんにちは。スライドシェアして大丈夫でしょうか？
大丈夫です。
じゃあ、この状態で時間までいいですかね。
Okay, it's time. So we will continue the lecture. So next lecture will be given the Professor Hanawa of Tokyo University under the title of HPC and AI Sharing from the University of Tokyo. He managed the Information Technology Center of Tokyo University. He is head of Operation Support Department at JCHPC。それでは講演を続けさせていただきます。次の講演は、東京大学の、花輪教授から、HPC-AI、Sharing from University Tokyo というタイトルでご講演をいただきます。彼は東京、大学、情報基盤センターの管理をされており、さらに JCHPC で運用支援部門の部門長でもあります。So, Hanawa, Professor Hanawa, please start your speech.
Okay. Thank you for introduction. So my name is Toshihiro Hanawa from University of Tokyo. So I will explain our activities and efforts on HPC and AI at our university. So we are the supercomputing center of the National University. We operate 3 supercomputer systems, and we have over 2,600 users. And so the first one is a read-bush system, which consists of the Intel Broadwell and the NVIDIA P100. And this is our first GPU system. And the second one is our Forest Park system, which consists of the Intel Xeon Phi night landings with 25 petaflops peak performance. And so actually, this system is operated by JCHPC under the collaboration with the University of Tsukuba. And the third one is Oakbridge CX using Intel Xeon Cascade Lake CPUs. So today, I will talk in detail of the read-bush system. So this system will retire soon, in this November. And as I mentioned, this system is our first GPU system. So during procurement this system, we discussed the researcher from the data science and the deep learning, to promote new type of users other than the traditional CSC field. And finally, we called this system officially Integrated Supercomputer System for Data Analysis and Scientific Simulations. And we decided to introduce the GPU, actually the P100. And also in our users, University Tokyo Hospital, and we realized very higher security system to promote this kind of research. So they developed the computed assisted medical image recognition, and we introduce dedicated login node for these project users, and they use VPN between our center and the University of Tokyo Hospital for isolation with the other project. Okay, so this pie chart shows us research areas based on the CPU hours on read-bush. And the left chart shows the usage of read-bush U. So this system equipped with only CPUs. So the computational science, such as simulation in engineering, earth and space science, and material science, are the typical area of users of our traditional supercomputer systems. On the contrast, right figure shows us read-bush H, with GPU part. So large portion are occupied by the information science related to AI and the bioinformatics, such as genome analysis and the medical image recognition by machine learning. And this chart shows us usage of the Oak Forest Parks and Oakbridge CX. these are the many core based or multi-core based cluster system. And so as you can see, the CSE applications are still dominant, but data analytics and the simulation bioinformatics, including medical image recognition, are increasing. Okay, so as you know, recently, Society 5.0 is proposed by Japanese government, aiming super smart and human-centered centric society by digital innovation, such as IoT, big data, AI, etc., and the integration of the cyberspace and the physical space. So toward Society 5.0, we are thinking about integration and the convergence of the simulation plus data analytics plus machine learning to support new type of workloads. So based on the knowledge of the solid bush, in addition to traditional CSA applications. So our approach is based on the AI for HPC or sophisticated simulations. So we are now introducing the two platforms for integration of the S plus T plus L, which will start operation soon in this spring. So one is a BDEX system. The official name is Wisteria BDEX01. And so another one is a data platform. Official name is MDX. So I will explain in detail of the BDEX and MDX from now. Okay, so as a Professor Boku already mentioned, so that we will introduce Wisteria BDEX01 in very soon. So this system will be installed by Fujitsu, and so this system consists of the two type of node groups. One is a simulation node named Odyssey. So this is actually the a mini Fugaku system with a 20 rack. So the 1/20th of the Fugaku system. And so another one is a data running node named Aquarius. This is also based on the GPU clusters with 100 GPUs per node with a 45 nodes. So the roughly simulation node will be 80%, and also data running node will be 20% of the peak performance. And also the data and running node can be connected to the external resource directly. So this is a system overview. And so totally Odyssey and Aquarius are combined with InfiniBand as an interconnect and share two kinds of the file systems, including the fast file system using NVMe technology and the shared file system, and also the other management servers like login node and job scheduling servers. So Wisteria is also actually comes from the legend of the Princess Wisteria. So Wisteria, in Japanese Fuji, and also as you know, the Odyssey and Aquarius come from the call sign of the Apollo 13th. So we hope that this system can save our life from the current very difficult situation of the COVID-19 pandemic. Okay, so this chart shows us how we utilize the BDEX system, Wisteria BDEX system for integration of the simulation data and running. So this is one possible application for integration of the S plus T plus L using the H3 Open BDEX. So H3 Open BDEX is also utilize libraries for the BDEX system. So the one typical application is also earthquake simulation. And so we also studied collaboration with Earthquake Research Institute, University of Tokyo, for earthquake simulation with a real-time data simulation. So currently we are prototyping using Oak-Beach CX system, which equipped the external Ethernet connection partially, and so that we can extend this idea to real-time disaster simulation such as a flood and tsunami, and also that we can apply this integration to the existing simulation code such as OPFORM. Okay, so this slide overviews of the 3D earthquake simulation with a real-time data observation and simulation. So JDXNet is a observation data exchange and distribution network in Japan, and so that we can get the seismic observation data from this network. And so we utilize real-time observation data, including satellite data of JDXNet through SciNet. And so this application will be for safer evacuation in case of emergency, improvement of and also the improvement of underground model by machine learning will be done under normal operations. Okay, so this is another example in the hierarchical data-driven approach based on the machine learning for integration of S plus this plus L. So this slide is provided by our colleague Professor Shimokawabe. So he is aimed to solve the flow around the circular cylinder, and acceleration of the transient CFD simulation using machine learning. So as a result, they can predict the behavior of the flow using the CNN prediction. So like this. So like this part shows us ground truth, and this is a prediction. So as you can see, the almost same tendency by the training data. Okay, and so this is another story. So MDX. So MDX is infrastructure for leveraging data. So this system is designed by the jointly by the 9 national universities and 2 national institutes. And so our plan is enable the real-time data processing platform on demand. So user can easily enable the isolated platform over the wide area network like this. So this is overview of the infrastructure of MDX. So MDX is consists of the 2 parts. So one part is CPU only part, so including the Intel Xeon Ice-X CPUs, and the second part is GPU clusters. This is just almost same as Aquarius of the Wisteria BDEC01 with 14 nodes. And actually, this system will be located in the same place of the Wisteria BDEC01, and also in the same campus, ABCI system also is located. And so in this system, several kinds of the storages to utilize for the internal data, so fast storage and the internal storage, and also the shared object storage. And so very small portion of the cold storage using the optical disk drive. And so we are very carefully designed for the security in this system. So we decided to separate network for the front-end network and the back-end network and also storage network. So in this system, so we plan to operate a cloud-like manner, so that we introduced VMware as a virtual machine hypervisor. Okay. And so this is one typical application for the MDX. So actually, so this project is performed on the read-bush system, as I mentioned. So this is medical image recognition by University of Tokyo Hospital. So they are developing the computer-assisted detection system, and so they would like to improve the hyperparameter using the auto-tuning platform for the better assisted application. So in that case, so we construct this kind of Bayesian optimization mechanism. So the automatically parameter will be selected. So better parameter will be selected and also trained. Okay. So as a result, so they can achieve very good results using the asynchronous parallelism using the Bayesian optimization for the lung mass detection in the chest radiographs. Okay, so summary. So I explained the three kinds of the supercomputer systems. So read-bush was the pioneer of the S plus D plus L like platform. But so this system will retire soon in this November. And so the success of the read-bush, so this is a real system to solve this kind of problem. So the support AI for HPC system. And also the MDX is much more practical application to enable the easy to deployment of the test environment using the wide range of network and HPC computation resources. Okay, thank you very much.
Thank you very much, Professor Hanawa-san. Hanawa-san 先生、ありがとうございました。Sorry, the time schedule is delaying, so I go to the next lecture. If you have any question, please write in chat. Okay, next lecture will given by Dr. Date of Osaka University under the title of Overview of Squid and Onion. He managed the Cyber Media Center of Osaka University. 次のご講演はです。大阪大学の、伊達先生の方からですね、サイバーメディアセンターのデータ集約基盤オニオンとスーパーコンピュータースクイドの概要ということで、ご講演をいただきます。彼は現在大阪大学サイバーメディアセンターの運用管理をされております。それでは、伊達先生、よろしくお願いいたします。So please start your speech, 伊達さん。
すみません、聞こえますでしょうか。はい。
はい、Yes。
すみません、岩谷さん、私、日本語で喋ってもいいですかね。
はい。
皆さん、みたいなんですけど。
はい、はい、はい。
本当にいいかしら。ちょっと不安になってるんですけど。
大丈夫です、大丈夫です。
すみません。じゃあ、日本語で。
This speech, Japanese speaker. Yeah. いや、もう言ってあるので。
そうですか。そうですか。ありがとうございます。はい。すみません。じゃあ、早速、説明させていただきます。スクリプトとオニオンの概要ということで、説明させていただきます。で、スライド変わりましたでしょうか。はい。いいですか。
大丈夫です。
はい。最初にちょっとお話しさせていただきますと、今、大阪大学のそのスクイットというスーパーコンピューターは、2021年5月に稼働予定で、今現在、そのための設計構築を進めている状況です。ですので、今日ちょっと発表させていただく内容は、一部未確定のものを含んでいて、変更の可能性がありますので、すいませんが、その点はご了承いただければと思います。で、時間も限られてますので、次に行きます。サイバーメディアセンター大阪ユニバーシティというところがありまして、で、実は結構サイバーメディアセンターというと、スーパーコンピューターって持ってるんやっていうことを言われたりとかするので、やっぱりちょっと言っておきたいんですけど、大阪大学にも計算機センターっていうのはありますと。で、その中で、研究とか教育とかを支える情報基盤の整備だとか運用を担うとともに、大規模計算、情報システムおよび ICT 技術を活用した教育に関する最先端の研究開発を推進するというのがミッションになっておりまして、でその中の一つの事業としてですね、全国の大学の研究者が学術研究、教育に伴う計算および情報処理を行うことができるよう、さまざまな高性能な計算機システムを提供していくというのを、一つのサイバーメディアセンターとしての業務となっています。で、現在はそのサイバーメディアセンターのその高性能計算環境はどんなものがあるんですかっていう話なんですが、今、ご存知の方も多いのかもしれないですけど、今はそのベクトル型スーパーコンピューターというのがありまして、NEC 製の SXS システムというのが動いています。で、また、オクトパスと言われる、その全国共同利用大規模並列計算システムというもので、動いているものがあります。で、今日お話しさせていただきますのは、このベクトル型スーパーコンピューターは2014年からの12月ぐらいから動いてたと思うんですけれども、動いてたはずですが、それがリプレイスをされて新しいスーパーコンピューターになりますので、そのお話の頭出しをさせていただこうかと思っています。で、スーパーコンピューターなんですけれども、このスーパーコンピューター、すでにもうオクトパスというのがあるので、このスクイットというスーパーコンピューターという名前を付けました。この略を探すの結構苦労したんですけれども、いいのが見つかったかなと思っていまして、で、一応思いといたしましては、我が国のその学術だとか産業を支える研究者による未解決のその、データサイエンス問題っていうのを探求支援するために、高性能計算だったりだとか、ディープラーニングだとか、マシンラーニングだとか AI だとか、そういったことを駆使するような高性能データ分析分野の計算ニーズを収容可能なクラウド連動型スーパーコンピューターとして構築したいと思って、2年間ぐらい調達を進めてきたものがこのシステムになります。で、特徴と、いたしましては、やはりその多様な計算ニーズをやっぱり入れないといけないので、本当に大規模な計算をなんかしたい方とかにはちょっとハイブリッドになっちゃうとできないぜって言われちゃうかもしれないですけれども、一応大阪大学といたしましては、3種混合のハイブリッド構成で、それこそワクチンみたいな名前になってるんですが、このようなシステムを、提供させていただくことになっています。で、ノード構成といたしましては、CPU、GPU、ベクトルの3種構成で、ストレージは20ペタバイトのそのハードディスクドライブと、あと SSD の 1.2 ペタバイトというハイブリッドで構成していまして、それらをHDR ですね、でまとめ上げるというようなシステムになっております。で、概要としては、これはまだそのシステムが動いてないもので、提案書をそのまま取ってきたものなんですけれども、真ん中の方にありますように、その相互結合接続網として、HDR200 ギガを中心に持ってるんですけれども、それをCPU ノードは1520ノードで、GPU ノードは42ノードで、ベクトルノードですね。これは後でまた説明いたしますけれども、そういうものが36ノードぶら下がっていて、 で、それらが左の方にあるファイルサーバー、21ペタぐらいあるそのストレージにつながっていると。で、その上に実はそのクラウディアンハイパーストアっていうそのオブジェクトストレージというものがありますが、このあたりも少しちょっと新たなチャレンジとして今回導入をしてやろうとしています。で、そのスクイートのその CPU ノード、自体に関しましてお話ししますと、あんまり言っちゃいけないこともあるって言われててあんまり言えないんですけど、新しいアイスレイクと言われるインテルさんから来ているプロセッサーが2機搭載された今見ていただいているようなブレードというか、そこの中に構成されるノードがあります。この NEC-LX103BJ8 というそうです。で、これに256GB のメモリと、ローカル SSD とストレージとして 240GB の SSD と、あと 200GB のHDR ですね。HDR の接続を持ったものにセントースを入れて、運転をしようというような感じで考えています。で、構成としましては、これを例えばこの 8U の1シャーシのものがあるんですけど、ここにはその20枚刺さるんですけれども、そこに搭載してですね、で、それを4ラック重ね、4シャーシ重ねて1ラックにして、これをですね、20ラックですね、集めることで、提供ユーザーに提供しようと。で、ここで20ノード乗っかるんだけども、19ノードっていうのは、ちょっと CDU とかの関係で1ノードはちょっと効率的な問題で抜いて、19かけることの、4×20 みたいな形で1520ノードになるという構成を取っているのが CPU ノードです。で、CPU の詳細はまたもう少し後になったら公開していきたいと考えているもので、今はすいませんが、ちょっとまだ公開できない、情報になっています。はい。で、GPU に、関しましては、やはり学内におきましても、やはり普通にHPC で使われるユーザーの方もおられるんですけど、やはり AI だとかディープラーニングだとかで、もう皆さん GPU とにかくないと困るのだっていう声も増えていますので、今回導入させていただくことになったものです。で、今回導入される、そのスクリプトの GPU に関しては、LX106RJ4G と言われるもので、その 4U のそのサーバーの中に、アイスレイクが先ほどの CPU ノードと同じ、CPU が入り、メモリとしては CPU よりも少し大きな512ギガのメモリが入ると。で、ローカルストレージは240ギガという感じになっていますが、ここにA100 ですね、最新の GPU が8機搭載されて、それを先頭して動かすという構成になっています。で、構成としては、これ、シンプルな図で、あれなんですけど、6ノードをこの1ラックに搭載してですね、これを提供するというような形になっていて、スクイットには、ごめんなさい、ちょっとスクイットの GPU に対して7ラックですね、提供することによって、CPU としては 84CPU で、GPU としては、簡単な計算で、8GPU×42 ノードで336枚を提供するというようなシステムになっています。で、ちょっと、このあたりは皆さん多分ご存知だと思いますので、ちょっとスキップしていきますが、この、GPU ノードの構成もこんな形で、デルタと言われる開発コードデルタと言われる GPU の8枚出しのものが入っていて、NV スイッチでちゃんとサポートしていますよというような図になっています。このあたりももう多分もう出てると思いますので、ちょっとスキップします。で、ちょっとここら辺がちょっと今日出たか、話として出てるかどうか分かりませんけど、多分出てると思うんですけど、スクイットにはベクトルノードというのがございまして、大阪大学はやはりベクトルノードを使ってきているユーザーさんは、そこそこいますので、それをサポートするというか、それをサポートするようなシステムが入ることになりました。でそれが、36ノード、入るという話なんですが、今、この、見ていただいているような、この VE タイプ 20A と言われるものが、を搭載したサーバーが入ってきます。で、サーバーにすると、この赤い、20A ってやつが、この 2U のサーバーの中に、8台入っているようなものがあって、これを多分1ラックにですね、18台収納してですね、それを2ラックという形で今回導入することになっています。あれ、動かない。 ですね。で、この写真は、昨日、サーバールームに行って撮ってきたもので、ほやほやなんですが、今のそのスクイットの導入状況というのは、実はこれぐらいしか写真撮るものがなくてですね、昨日やっと撮れてよかったとは思ってはいるんですけど、こんな形で、18ノードをこう1ラックにして、それを2ラックと。で、それはすべてその水で冷やして提供するというようなシステムになって準備をしている、ところでございます。で、これは、先ほど言いましたように、1ノードあたりに対して、8 GPU 入っていますので、これを36ノードということで、288VE という形で、この赤いのが288個入るような構成になっています。で、これもブロック図はこんな風になるんですけど、CPU としては AMD のその ROM と言われるその EPIC が入っていて、でこれをPCI Gen 4でIB のインフィニバホストチャネルアダプターにつながっているわけですけど、2つ口を持っています。で、ベクトルエンジンは8枚刺さっているような形になっています。で、このスクイットのそのベクトルなんですけども、これは、左下の図がありますように、そのアクセラレーター型って言われるものは、いわゆる GPU の処理で、アプリケーションから必要に応じて、その、アクセラレーターの方に一部の処理をオフロードして、処理をして戻ってくるというようなことを繰り返すようなパターンの動きになるんですが、このスクイットのベクトルマシンの方でいくと、SX オーロラ翼の特徴になるんですけれども、これは、ベクトルエンジンというものが、そのカードみたいに見えるんですけれども、そちらの方でプログラムを実行すると、アプリケーションはベクトルエンジンでとにかく動くと。で、IO が発生すると、86プロセッサーの方にオフロードして IO 処理を行うといったような形になっていて、利用者からはプロセッサーとして使うことができるようなシステムとして、提供されるものとなっています。で、さらにですね、この新しい世代からは、これまでその SX 系のシステムだと、オペレーティングシステムも独自のものだったんですが、今回のシステムからは Linux として提供されるシステムになりましたので、Linux のその既存資産利用という、既存資産を利用しながら、ベクトルのその特徴を使えるというような、そのハイブリッドなアーキテクチャっていうので、ノードとして実現できています。で、これを36ノード提供するという形になっています。ちょっと時間が気になってきました。すみません、ちょっと急ぎますが。で、このスクイットのインターコネクトは少しちょっと新しいことにチャレンジをしています。で、その、新しいことといってもそんな新しく、皆さんの前では多分あんまり新しくはないのかもしれないんですが、CPU ノードのその1520ノードというものを、その、3つのグループに分けまして、で、494のノードのグループと513ノードのグループに分けて、で、これをそれぞれファットツリーで構成、フルバイセクションのファットツリーで構成して、それらを、相互に、グループを相互に接続して、するようなドラゴンフライプラスっていう、その、トポロジーに、CPU ノードはしております。で、一方で、A 群 B 群点書いてあるのは、GPU とベクトルノードのことなんですけれども、こちらの方は一つのそのファットツリーとして、ファイルシステムとも接続して、この併用、2つのそのトポロジーを併用するような形で、システムを組んでいます。で、スイッチには、メラノックスさんの、QM8700 というのを、ファットツリー側には確か7個を使って構成をしているというような構成です。CPU の、詳細に関して説明すると、このような形になりますが、先ほど説明した通り、グループごとにフルバイセクションのファットツリーを構成して、ユーザーはこの規模では、特に帯域とかのボトルネックを気にせずに計算できるように、構築を進めているという状況です。で、グループ間は、ですね、各グループに対して200ギガの、HDR を95本ずつこう出すっていう形で手を組ませて構成しているというもので、ファイルシステムに関しては、36本の線を流し込んでいるというような構成を作っています。はい。で、ベクトルと GPU に関しては、ファットツリーで作っていまして、作る予定で進めていますと。で、これも、絵に描いた餅の状態になっていまして、昨日の状態、ちょっとどんな感じかなと思って見に行ったら、右側にある写真のように、何も繋がってないようなスイッチだけが転がっていたので、まだこういう状態で、というのが、現状のご報告です。はい。 で、そのスクリプトなんですけど、スーパーコンピューターを構成するっていうときに、少しちょっと面白いことをしようと思いまして、今回のそのスーパーコンピューターに関しましては、そのクラウドバースティングという機能を入れています。で、正直なところ、先に入れたスーパーコンピューターシステムのオクトパスというのが、やはり利用率が結構高くて、待ち時間が3日だったりとか、場合によっては1週間ということが結構あって、利用者からのいろいろちょっとクレームというか、こともちょっと増えてきましたので、やっぱりクラウドをちょっと使わせてもらいたいなということで、いろいろチャレンジしています。で、我々としてはですね、やはりユーザーさんが、やはり待ち時間が増えてきたときに、このクラウドをオンにして、で、ジョブを流したいと。で、待ち時間が減ってきたら、クラウドから撤収して、オンプレミスだけ使わせたいみたいなことを実現しようと思っていまして、今回そのような仕組みを、導入して、スクイットでは運用する予定でいます。で、今後としては、例えば、今回のシステムだと、AMD さんのチップとかもなかったりしますので、新しいチップが出てきた時とかに、そういうものを試験的に利用者に対して早期配備して提供するだとか、そういったことに使っていきたいというような計画で今、設計を進めています。はい。で、最後のこのトピックになるんですけど、ちょっと時間があれですけど、オニオンというデータ集約基盤っていうものを今回やろうと考えています。で、オニオンの背景にありますのは、大阪大学のその方向性というか、ビジョンというものがあるんですけれども、研究データをきちんと責任を持って管理しようという話とともに、きちんとそのデータを活用した研究を、産学競争、国際共同研究でちゃんとやっていこうということが打ち出されていますので、そういったことを支えるデータ基盤というものを作りたいということで、今回この大阪ユニバーシティネクストジェネレーションインフラストラクチャーフォーオープンリサーチ&オープンイノベーションという少しちょっと強引な略ではあるんですけれども、そのような基盤をの構築を今回のそのスパコンで目指しています。で、今のところ、これが簡単なポンチエの図ではあるんですけど、ポイントとしては、要は左側にあるその並列ファイルシステムと右側にあるオブジェクトストレージというものをうまく連動させて、ユーザーさんが例えばクラウドにデータを置いて、で、海外の研究者と共有する。で、海外の研究者から提供されたクラウドのデータを、スパコンの中に取り込んで計算する。で、そしてそれが終わったら、またクラウドに出すみたいなような、ちょっと空港的なイメージのそのデータ基盤っていうのを考えて、設計を進めています。で、その DDN さんの方のクラスター、ごめんなさい、ファイルシステムに関しましては、これは、DDN の初めさんという方から借りた図なんですけど、なんでしょうかね。普通のその、ラスターファイルシステムで、多分その SSD っていうのがちょっと搭載されているところは、ちょっと新しいところで、判断にとっては新しいところで、今回、その一つのチャレンジは、S3 に対応する、そのサーバーを一つ持たせています。で、この、また、オブジェクトストレージ側は、クラウディアンさんのそのハイパーストアっていうもので、S3 に対応して、そのオブジェクトをこう蓄積するような仕組みがあるんですが、現在まだこれもまだ来てないのであれなんですけど、今は、こんな状態で、今、設計を進めている、ところになっています。で、この仕組みとしましては、このデスクトップって書いてあるところがユーザーが、いると考えていただいて、で、この、Next クラウドというので、ウェブインターフェースを提供しながら、この外部ストレージ機能っていうので、例えば、クラウドストレージだったり、今回導入したラスターのその S3 のサーバーをこう見えるようにしたり、クラウディアンさんのそのオブジェクトストレージを見えるようにして、ユーザーからはそれをわからないようにして提供すると。で、ユーザーは S コピーだけじゃなくて、ウェブインターフェースを通じてデータを動かせるような仕組みを現在その設計をしてやっております。で、本日のまとめなんですけれども、まだ設計中というか、まだものがないので、あまりいい発表ができなくて大変申し訳ないんですけれども、2021年5月にそのスーパーコンピュータースクイットというのを大阪大学として提供していきます。で、これはその高性能計算、データ分析分野の計算ニーズを収容可能な3種混合なハイブリッドスーパーコンピューターとします。で、クラウドの機能も取り込み、高負荷時だったり、新しいそのプロセッサーが出たときとか、アクセラレーターが出たときには積極的に取り込んでユーザーに提供していくような仕組みをチャレンジしていきたいと考えています。で、またデータ基盤というものを、オニオンというものを構築していまして、ただのSコピーとかではなくて、利用者のその利便性を考えて、S3 に対応させて、 データがシステム内から外から中へ動くような仕組みを構築していまして、残念ながらこれは構想でしかないので、お恥ずかしい限りではありますが、現在作業中となっていますが、このようなシステムが入ってきますので、またこのようなお話をいただければ読んでいただければと思います。以上です。ありがとうございます。
ありがとうございました。伊達先生、貴重なご意見というか、レクチャーありがとうございます。それでは、Thank you for that, Dr. Date. So please go, we are going to next lecture. So next lecture is will given about Fujitsu HPC and AI technology by Dr. Nakashima of Fujitsu Laboratory. Fujitsu is one of the leading supercomputer vendor in the global HPC. He is involved in research on the HPC and AI technologies. So, Date-san, sorry, Nakashima-san, please start your speech. Sorry.
Thank you for the introduction. ありがとうございます。画面見えておりますでしょうか？
はい、大丈夫です。
はい。
スライドモードっていうか、スライドショーモード、はい、OK です。
大丈夫ですか？はい。富士通研究所の中島です。本日はこういう機会いただきましてありがとうございます。並列化の技術に関して、ご紹介させていただければと思います。So today I'd like to share our parallelization technology for the large-scale DNN workload. So at first, as you know, for recent several years, AI technology has been significantly developed, and the complexity of the training neural network continues to increase. So this graph shows the computing demand on the AI workload. A vertical axis means petaflops day means amount of the computation AI workload required. If AI workload consumed 1 day by a 1 petaflops machine, this workload is plotted at 1 petaflops a day. A horizontal axis means the years. So this graph shows computing demand of the AI increased about 300,000 times for these 5 years. And so computation for the AI requires huge computing resources. On the other hand, Moore's law can only supply the double computing power per 18 months. So you can see the slope, the difference between the complexity line, this pink line, and this green line. So to overcome this large gap, we research and develop the parallelization technology for AI. For this huge computing demand for AI, Japan has several supercomputers. I would like to introduce the 2 supercomputers, ABCI and Fugaku. ABCI is constructed and operated by the AIST and manufactured by Fujitsu. ABCI has designed for AI, so each computing node has 4 volt GPUs. The total number of the computing nodes is 1,088, so a system has more than 4,000 GPUs. It's a very good infrastructure for AI. Fugaku is developed by Riken and Fujitsu, is general purpose supercomputers. Currently, Fugaku is number 1 in top 500, and HPCG, HPL-AI, and Graph 500. It means that Fugaku will resolve the various kinds of the heavy workload, and not only the HPC simulation, but also the AI. Especially some recent HPC applications use AI for data analysis or find some scientific result from the huge data generated by HPC applications. So these kind of the HPC and AI combination will run efficiently on Fugaku. A computing node of the Fugaku has a 1 A64FX processor, of which performance is 3 teraflops in double precision. Totally, Fugaku has more than about 150,000 CPUs connected by a TOFU interconnect. So in order to run the AI workload on supercomputer, the workload should be parallelized. Basically, there were 2 strategies, data parallel and model parallel. In data parallel, the entire data set is divided into the sub-data set, and the training process on each node runs the sub-data set by forwarding and backwarding processes. After several forwarding and backward processes, all release exchange and aggregate the weight information in order to merge the training result. Data parallelism iterates this training and all reduce, and finally the process generates the trained model by entire data set. However, the cost of the all reduce is very low compared to the computation cost. So communication overhead is relatively small. However, the data parallel approach has some kind of a limitation with the total number of the CPU or GPU by milliverse size limitations. In order to enlarge the number of the computing nodes, we have to enlarge the milliverse size. But also, large milliverse size reduces the accuracy. So I will explain the detail in later slide. Another approach is model parallel. In model parallel, several nodes computing a single training task, as same as a conventional HPC parallelized applications. Each computing node calculates the part of the neural network with halo exchanges. This cost of the halo exchange is very heavy, so it is not so easy to accelerate the total performance with a model parallel. We should apply the model parallel method with careful design to avoid the heavy communication overhead. Today, I'd like to share the two our research works. One is research for the acceleration of the image classification. We apply the data parallel and evaluate it on ABCI. Another is ML powerful HPC challenges. We apply the both data parallel and model parallel technologies, and we evaluate this on ABCI and Fugaku. At first, I would like to explain the acceleration of the image classification workload. This workload uses the ResNet 50 and ILSB RC 2012 dataset. We have already disclosed the detail of this work at HPDC 20, so please refer it for detail. Stochastic gradient descent update in deep learning is a very iterative method. So if we can update weight parameter many times, we can train the higher accuracy the model easily because we have many chance by many updates. So the number of the iteration is very important for the accuracy. The minibatch size is a data size for the unupdate. For example, if we use 2 GPUs for the training and the minibatch size is 4, each GPU trains by 2 images. If we use 4 GPUs, in this case, each GPU can only handle the single images. So we cannot increase the number of GPUs more than 4 if minibatch size is 4. Large minibatch size improves the throughput of CPU and GPUs because it can assign the larger number of the images to a single GPU or CPUs. However, if we increase the minibatch size, the number of the iteration becomes small. For example, ILSBRC dataset has a 1.28 mega images. So in this case, if we set the minibatch size to about 80,000, one epoch has only the 60 iterations. So this is very difficult to keep the high accuracies. So large minibatch size can enlarge the CPU and GPU and achieve higher throughput, but the accuracy becomes low. as this graph shows, if we use many GPUs to accelerate the performance, the minibyte size should be large. However, the minibyte size reduces the accuracy. In order to prevent this loss of accuracy, several related work are proposed. For example, the LAS, the level smoothing, warm-up, and so on. So today, I'd like to show our proposed new method to keep this accuracy. In this slide, I would like to explain our proposed method. Data augmentation technologies enable the recognition of the various images and improve the validation accuracies. Here is augmented images. So you can see that these images are cropped or mirrored from the original images. Data augmentation creates many images variations, it improves the accuracy. This technique is widely used for the image classification. However, the data augmentation needs more iteration to convert the means and the variance value in batch normalization layers. Because the means and the variance are different between the original image set and the augmented image set. So we propose a final polishing method. This method turned off the data augmentation during the training. And the turning off is performed near the end. And this method helps to convert the means and the variance for original image dataset. It improves the validation accuracies. So this graph shows the relationship between the turned off epoch and the accuracy. You can see the best case is turning off the data augmentation around the 85th epoch. We apply the method for the acceleration using about 3,000 GPU environment. Here is our parameter configurations. We set the turning off epoch to 85, and minibus size is more than 86,000, a very huge minibus size. This configuration achieves more than 75% at 19th epoch. And we completed the training in about 60 seconds with 3,000 GPUs. Our proposed method enables more than 86,000 milliwatt sizes. Comparing with other works, we can see that our result achieves a huge milliwatt size with a good validation accuracies. And the huge milliwatt size achieves 1.03 minutes result. So this result was measured in June 2019. At that time, the performance is best in the world. Currently, Google and NVIDIA renew this performance value, and so they achieve less than 1 minute result using the TPU and Ampere architectures. However, this result remains the highest performance using the V100 architectures. Next, I would like to share the MLPerf HPC challenges. We have already released the following press releases, so please refer it. And we tackled this research challenge by the research collaboration with RIKEN for Fugaku and AIST for ABCI. Thank you for the research collaboration. MLPerf HPC is a huge AI workload provided by MLPerf communities. They are the AI workload for HPC simulations, and the first version was released in November 2020. Basically, the benchmark score is the elapsed time of the to reach a defined accuracy with a given workload. So this problem is a kind of the strong scaling problem. And so MLPerf HPC version 0.7 has two workloads, CosmoFlow and DeepCam. So CosmoFlow is a 3D convolutional architecture trained on some cosmological simulation data. And the DeepCam is a convolutional encoder-decoder segmentation architecture trained on some climate simulation results. Unfortunately, I don't know the detailed meaning of the cosmological simulation and climate simulations. But also I can recognize these workloads is very huge. So data size is 5.1 terabyte or the 8.8 terabyte. So we should accelerate by the parallelization technologies. This graph is a MLPerf HPC result. 6 leading research institutes in HPC submitted the performance result. TACC, NASC, NCSA, PITSDynit, ABCI, and Fugaku joined this performance competition. The vertical axis means elapsed time of the benchmark, so lower is better. We apply the data and model power technology to accelerate the performance, so we can get a very good result. As I explained the former slide, large minibus size challenge is very important to achieve the higher scalability by data parallel. MLPerf HPC performance is elapsed time to achieve the defined accuracy. So loss of accuracy by large minibus size increases the number of the epoch, and this makes performance down. This figure shows the relationship between the batch size and the number of epoch. So case A is a kind of these versions. I suppose the number of the epoch is 100 and the elapsed time is 100 in case A. If so, please focus the case C. If we set the minibus size to 1024 and in this case, the number of the epoch becomes 300. We can estimate the performance elapsed time of this benchmark around 185. Because a larger number of the epoch increases the elapsed time, but twice batch size can increase the throughput using the double computing resources. Unfortunately, in case C, the performance of the case C is less than case A. But if we suppress the increase of the number of the epoch, such as case B, we can boost the performance. So hyperparameter tuning is very important. We tuned the hyperparameter for large minibus size. This graph shows the minibus size and the number of epoch in all results of the HPC MLPerf HPC version 0.7. So, and the result marked by the dashed rectangle are our results. And the vertical axis is a number of epoch to reach accuracy criteria. So as overall tendency, the number of epoch increases as minibus size increases. And so we could increase the minibus size to 4096 with a number of epoch less than the 160. It is a 4 times larger batch size with almost same number of epoch compared to the Corey-KN result. And we also we achieved the 2048 minibus size with almost the same number of epoch compared to the 512 batch size. So our hyperparameter tuning method could enable to use a large number of the computing resources. In previous slide, we enabled the minibus size up to the 4000. But it means that we can only use 4,000 CPUs. 4,000 is not large enough for Fugaku. So we tackle to implement the model parallel method for Fugaku. Comparing the data parallel, the model parallel approach has to overcome the heavy overhead of the Halo exchanges. So we have to choose where the model parallel applies with careful designs. For example, the neuron nodes in full connection layers are tightly connected. So cost of Halo exchanges are quite heavy. So it is not good design to apply the model parallel to full connection layers. On the other hand, 3D convolution layer in CosmoFlow is relatively more loosely connected. So we implement the model parallel for 3D convolutions. This less overhead implementation for 3D convolution realizes a 1.7 times faster result with 4 times larger number of CPUs. Of course, 1.7 times is not so good, so we will continue to tune up our implementation. Finally, we run a single training task with more than 60,000 CPUs by hybrid parallelism on Fugaku. I think it is a remarkable achievement in our MLPerf HPC challenge. Again, I would like to confirm our result of MLPerf HPC. In GPU system, BCI achieves a 20 times faster result than NCSA. And in CPU system, Fugaku achieves 40 times faster than Core KNL. So this result shows a parallelization technology and HPC system accelerates the huge AI workloads. Last, I would like to summarize my presentation. In order to provide the computing power for the heavy AI workload, we research and develop AI acceleration technologies by large-scale parallelism. So, and we continue to research and develop this area, not for only HPC, but also AI. Our supercomputing technologies will continue to explore the AI frontiers. Thank you very much. 以上で発表終わります。質問等、後になるかとは思いますけれども、日本語でもあれにしますので、どうぞよろしくお願いいたします。
ありがとうございました。中島先生。Thank you for Dr. Nakashima. So, I would like to continue the next lecture.